Thanks a lot for the kind introduction and also a warm welcome from my side. I'm delighted to open up today's first focus topic session on dynamic risk management. And instead of giving a detailed talk about our own work at Fraunhofer when it comes to dynamic risk management technique, I want to rather use the next 15 minutes to give you a high-level introduction into the dynamic assurance field, so motivating why we are actually needing dynamic assurances in the context of AV safety, and hopefully the resulting high-level classification structure sets the stage for the upcoming technical talks and provides also basis for the panel discussion. So let's start with the fundamental question: why is AV safety assurance actually so hard, and why is there a need for dynamic assurances? So one useful way to answer that question is to look at the requirements on how to assure traditional automotive systems. So traditional automotive systems are mainly support systems for human drivers, which supposedly have pretty short safety capabilities already, either through driving school or through evolution. So in effect, those humans, they perceive the world, they reason about the criticality of the situation, and hopefully take safe decisions. While only in certain constrained situations, the systems take over the safety responsibility. And this limited amount of real-world understanding required for the system to take safe decisions makes also the assurance task doable for the safety engineers, because the cognitive skills to anticipate the characteristics of the safety system-relevant world are actually quite manageable. And for this kind of task-specific automation, a lot of practical experience and methods already exist today. For instance, if we look at standards like ISO 26262. However, when we look at autonomous vehicles, several new problems emerge simultaneously. So the first obvious one is that the decision responsibility for what is safe and what is unsafe is actually shifting from the human driver to the system. And one consequence of this shift is that now the world understanding that is required in order to determine what is safe and unsafe in the first place is getting much more complex. So in a way, the real world and the system relevant world are both complex, but just in different ways. Another requirement or new challenge that emerges through this additional need to understand situations in a much better way is the use of AI technology that comes with its own huge assurance challenges, because it's a completely new way of developing software. So summing up, the task of an AV safety engineer could be done like: we need to assure a full responsibility intelligence in a complex context based on a very limited experience with technology and such complex worlds. So the consequence is a very high residual uncertainty about whether the system is actually safe at deployment. And one way to relieve the safety engineer from living with this burden and to also address the residual uncertainties at deployment, an idea could be to complement the design time safety assurance techniques with dynamic elements. So how could this look like? The general idea is the following. At design time, the safety engineer fires up a holistic safety case structure and collects evidence from the typical safety engineering activities at design time. The result is, on the one hand, a deployable driving system that, due to the challenges mentioned on the last slide, contains significant residual uncertainty with respect to safety. That's why, in addition to the driving system, a safety monitoring architecture is deployed as well, whose purpose may be twofold. Both purposes have in common that actually risk-relevant elements are monitored, and the runtime safety analysis activity infers these events into dynamic safety knowledge. On the one hand, this safety knowledge can be used to complement design time safety case structures with monitored risk-relevant events and the inferred knowledge, and in effect either increase the confidence that the assumptions were correct or raise issues that have not been anticipated before. This is sometimes also called safety DevOps or silent testing. The second way of acting due to this knowledge is to enable the system itself to take action through adaptation in response to changes in situation risk. This provides the basis to optimally trade off risk against utility at runtime in a sequential fashion. Let's structure and organize the assurance needs now in a bit more abstract fashion and clarify what we mean when we're talking about dynamic assurances. So one useful way to decompose this structure is to distinguish three criteria. When is an evidence produced? When is it consumed? So either at design time or runtime, and for which purpose is it actually produced in the first place? And if we are building, let's say, a matrix on top of the contents that we've seen on the last slide, then what we are coming up with is 4 quadrants. The first quadrant refers to design time evidences which are used during design time assurance, and this mainly boils down to creating a safety case structure and collecting evidence during the typical safety engineering activities that we usually see at design time. So meaning system safety analysis, hazard and risk analysis, design time verification and validation, and activities like that. The second quadrant is actually accounting specifically for the residual uncertainties that we usually have due to mentioned reasons. And here we are producing evidences at runtime, but they are in the end used at design time again. So this is basically then boiling down to assumption validity checking of assumptions of our safety case, and either gaining confidence through field feedback or finding out safety issues that have not been anticipated at design time already. The next quadrant kind of elaborates on that, because if we are building runtime monitors for design time assurance or for runtime assurance, as we will see in a minute, it is necessary in both cases to actually engineer them in a meaningful and in a sufficient way. And this boils down to creating design time evidence, but in this case for runtime assurance, so making sure that our runtime monitors work correctly and providing evidence for that as well. So this basically extends the top left corner, and with methods that kind of specifically analyze variability and build respective runtime monitors out of these risk variability. Last but not least, we are not only building runtime monitors to provide runtime evidence for design time assurance as shown on the top right corner, but what we also want to do in the future is actually providing runtime evidences for runtime assurance. And runtime assurance is effectively enabling the system to a certain extent itself to react to changing risk at runtime. And what this means is that in this quadrant we are having research challenges that are centered around creating uncertainty awareness for a system and enabling the system to manage the balance between safety and utility. And what I count as dynamic assurances right now is actually these 3 parts, which come on top of the usual design time evidences for design time assurance. So when we're looking into the design time evidence for design time assurance quadrant, some of the open questions and research challenges relate to how to actually build a unified safety argumentation structure that does not only consider this top left quadrant, but also all the other 3. So kind of incorporate in a meaningful way, like runtime evidences for design and runtime assurance, and also design time evidences for runtime assurance. Second challenge is related to kind of harmonizing the other 3 quadrants with established standards. So are there any kind of activities that can be shared between both of them, and where are the interfaces between the respective processes? So something that is in particular open is a kind of a definition of a globally acceptable risk definition, and a breakdown of this risk definition into quantitative verification and validation targets that can be possibly executed as much as possible in simulation, because otherwise we won't make it given the confidence requirements. When it comes to understanding and modeling, then I feel that a lot of research effort needs to go into a concretization of the concept of operational domain. So kind of something that is characterizing the world our system needs to understand and interact with, and the operational design domain as a construct to acknowledge for weaknesses that we are having, where we can say we have too high uncertainty, so we need to exclude certain situations and elements or scenarios from our operational domain, where we can say, okay, here we can guarantee with a sufficient confidence that our system is operating safely. So I believe that modeling techniques and reasoning techniques about operational domain, operational design domain is something where effort should be put in this quadrant a lot. So when we look at the quadrant where we want to produce runtime evidences for the design time, then there are like three big areas that we need to cover in research. First of them being like, how do we in the first place formalize the assumptions and build respective metrics to measure at runtime whether an assumption is valid or not. This may involve, for instance, checking whether actor behavior changes. For these kind of change detection, we need appropriate and realistic actor behavior models. We need to detect whether situation frequencies that we based our hazard risk analysis upon, whether these change either in favor of our risk assessment or against it. We need to detect events that relate to our system internals. For instance, how often our perception systems, for instance, disagree. This might be an indicator that something is wrong and we need reanalysis. If we detect edge cases, this is also something that we need to think, how can we detect things that we don't know we want to monitor in the first place. So apart from this what to monitor, we also need to get an idea and research both architectures and concepts on how to perform this monitoring in the first place, because it does not only involve like monitoring in our vehicle, but also how to react to a monitored event, for instance. So this means like covering the whole chain from my vehicle system that actually gets to know that an assumption may be invalid, or that a scenario or situation is interesting to be reanalyzed, then kind of communicating that back via V2X mechanisms to a cloud storage and the respective analysis backend system, where then a safety engineer or an organizational unit is triggered in order to kind of do something about that scenario, so reanalyzing and potentially developing a software update mitigating unforeseen safety issues, and finally kind of rolling out such an over-the-air update. You can imagine that actually this chain involves new challenges. For instance, we didn't have it so far that actually cloud systems became safety critical, but in this use case where we are kind of providing confidence from the field, this is indeed safety critical. So also we need to research methods on how to make cloud systems safe. And the third block is related to not necessarily to the development agency or the development company itself, but rather to the public, and building public trust and controlling whether like the governmental or regulatory target values for acceptable risk have been met. So there needs to be also research in how these data interfaces that the vehicle may expose to such public entities look like, and make sure that post-deployment the explainability of actions that the AV took is always given. When we're looking into the third quadrant, where we are dealing like with the design time evidences we need for building runtime assurances, we have to split also the research challenges according to which kind of runtime monitor we are building. When we are considering the runtime monitor is supposed to enrich and design time safety cases, one thing that is particularly important for research is the transfer of embedded system safety and security concepts and methods to cloud systems, and more specifically information systems. This is required to build up the whole chain that I have just described for this monitoring process from vehicle fleet to analysis backend back to the over-the-air updates. And yeah, there apparently the existing standards, they mostly apply to embedded systems, but not yet for information systems. So there is some harmonization required, also to promote process reuse as much as possible. The second point is that now that we are dealing or realizing a safety concept both with technical elements and with organizational elements, we get yeah, in a way a socio-technical safety concept. And yeah, what is quite new in automotive is not so new in other domains, like for instance the aviation or industrial automation domains, where this is already yeah, present for a long time. So yeah, one of the research fields that or research challenges that are current there is that kind of the methods are transferred for building and validating such socio-technical safety concepts. When we now look at the design time engineering and assurance for or the evidences for runtime assurance, where we are building runtime monitors that dynamically optimize safety and utility. This is also, by the way, the field where I'm particularly active through my doctoral studies. There, one of the key aspects of research at the moment is on how to analyze and formalize which kind of information human drivers process in which way to estimate and react to dynamic risk. So the results of these yeah, research activities are effectively situation-aware risk models, where it is known which situation cues actually lead to which risk variability and how to properly react and adapt so that the risk is always acceptable, which means in reverse that the utility is always like as high as possible given the safety constraints. Elaborating on this, we can also understand risk management or dynamic risk management on several levels. Yeah, for instance, on several time scales, where there is like, for instance, an operational level of risk management, where we say, okay, we can react quite fast to certain incidents. There's also like something that is more like proactive in nature, so where we kind of try to get an idea about risky situations that may happen like in the maybe next 5 to 10 seconds, if that's possible, and try to proactively avoid such situations so that we don't have to react with hard safety mechanisms and interventions. So, and the respective research branch is yeah, called Multilayer Risk Monitoring architectures, where we, in a way, it is tried to realize the yeah, commonly known Swiss cheese model in a dynamic way into the system. At this point, we assume we have a monitoring chain in place that perceives risk-relevant situation features in the traffic process, that infers a dynamic risk from them, and that knows how to adapt behavior to optimize safety and utility of the system in every situation. Now, we have to acknowledge that also these components may be subject to uncertainty. For instance, if adverse weather conditions lower the trust and perception, the inferred risk somehow inherits this uncertainty. So making such uncertainties explicit enables to dynamically determine whether the output of the runtime monitor and the resulting actions are as trustable as we would like them to be during driving. Thus, teaching systems to be uncertainty aware and know how much they can trust their own perception and reasoning capabilities is a key research topic to be addressed in the future. So, coming to the end of my talk, if I should pick 3 things that you should definitely remember from this talk, then it would be like the following 3. First, that residual deployment uncertainties really force us to complement static with dynamic assurances. So this means like that we definitely have to do something for safety also after deployment. Second, that dynamic assurances are always grounded in design time safety processes, and that they can either provide runtime evidence for complementing design time safety cases with field feedback, or that they enable the AV itself to trade off safety and utility using capabilities for uncertainty awareness. And the last takeaway from my side would be that considering the creation time, the consumption time, and also the purpose of use for runtime evidences as a rule of thumb to navigate both problem and solution spaces when people talk about dynamic assurances. And with this, I'd like to end my talk, and thank you for your interest, and I'm ready for questions either now or later on in the panel discussion.